Welcome to a new video. This time we're talking about something called inscribed angles. And in particular, we're going to be working with problems something like this, where we have a circle and then we've got a couple of angles that are drawn. Now the one angle right here is from the center of the circle. So not surprisingly, we're going to call that a central angle. Then this one right here that comes over and the vertex is actually on the circle, we're going to call an inscribed angle. And again, just remember, we did from before, right? Circumscribed figure is around another one, right? So this would be an inscribed circle, circumscribed triangle. Or if you flip it the other way around, here's a circumscribed circle. In other words, it's on the outside. Inscribed triangle, right? Before we were dealing with inscribed circles, now we're dealing with inscribed triangles, where the angles are inside the circle as opposed to outside the circle. Okay, so let's come back now to this example here we were just looking at. In particular, we're trying to find out what is the measure of R. Okay, so this angle right here, again, that angle, which as you just remembered from a second ago, I hope, we're going to call that a central angle, right? Central angle, right? The central angle is the one from the center, not surprisingly, right? Here's our central angle. Okay, now the other one, which is the new concept that we're really going to be working on more today, is what we're calling an inscribed angle. Okay, so again, let's get our terminology straight here. Inscribed angle, right? And the inscribed angle in this case is this guy right here, right? Which is angle S, central angle, angle R. Okay, now let's just kind of look at it and just sort of see, eyeball it a little bit. This roughly, not exactly, but sort of looks like a 90-degree angle. Not quite, but maybe a little less. And this 42 degrees, well, that's a little bit less than 45. It kind of looks like this yellow angle, the central angle, is twice as big as this red inscribed angle. So that turns out to be a thing, right? In particular, we've got a theorem for this. So I'm going to draw a few pictures here just to try to just sort of sanity check it a little bit, okay? And so this is a theorem we're going to be using today, which is the inscribed angle theorem. In particular, let's take a look at this. So we've got three circles. We're going to be using all three of these in a second here. And what I'm going to do is for each one, I'm going to draw a central angle, and then I'm going to draw an inscribed angle. But they're going to intercept the same arc. Okay. Okay, so let's start with this. So I'm going to start at the center, and I'm going to come out from the center like this. Boom, boom. Okay, now this special kind of little ruler here, this is exactly 90 degrees with a 45, 45. Okay, so this is 90 degrees. Okay, that's the central angle. Okay, now again, like I said, this is an isosceles triangle, so these are going to be 45 degrees. And sure enough, if I line them up like this so that it's exactly over these two spots that the radius and the other radius intersect the circle, look what happens, right? This is pretty cool. So this is 45 degrees for the inscribed angle, and the central angle on this side is 90 degrees. Sure enough, they're exactly differ by a factor of 2, right? The central angle twice as big as the inscribed, or you can think of it the other way. The inscribed is half as big as the central. Sweet. And that happens for a lot of different degrees and different angles, not just 90. Okay, we got a different triangle here, right angle triangle template. This one is a 30, 60, 90. Okay, so this time what I'm going to do is I'm going to have the central angle be 60 degrees. Okay, so this is 60 degree right here. And when I use my handy little template here, if I can pick up my pen, sure enough, watch what happens. So cool. And part of what I kind of like about this is one of those theorems that is honestly not one of those things that's just immediately obvious. I mean, when you draw some pictures, you start to notice that it's true. But I'll be honest with you, if I was just kind of playing around on my own, I probably wouldn't have just sort of figured this out on my own. I really needed someone to point it out to me. And then eventually I kind of saw that it worked. Sure enough, look at that, it did it again. It was so perfect. Look, here's 30 degrees, and then up here is 60 degrees. Look, it keeps working, right? And again, you can kind of think of it this way too, right? If this is 30 degrees, right? If I kind of split that in half, look, here's 30 and here's 30, right? Two of these little angles fit in the big angle. Same thing goes here. Two of these would fit into there. Finally, now, and this one's kind of a special one, right? Anytime you have a right angle, that's especially interesting. Let's finally look at this last special one that comes up a lot. And in particular, what this is I'm going to draw across here a straight angle. In other words, a 180 degree, right? So right there at the center, right, there's one ray, there's another ray, right? In other words, it's a straight line, okay? So that would be 180 degrees. And again, just bear in mind that the angle that I'm talking about is the one on top. This is the one on top. It's just the one, right? The angle I care about, notice that they're both, these angles are defining this arc up on the top. That's the defining feature of this. And just to be clear, this 60 degrees that I'm talking about right here, that's 60 degrees of the central angle. The measure of the arc also is 60 degrees, right? Because the measure of an arc is considered the same as the angle that comes from the center. All right, so now let's see, moment of truth. Here's a 90 degree angle here. Let's see if this would work. Does a 90 degree circle, or excuse me, a 90 degree angle exactly touch? This is going to be so cool. Watch, it's working. I love this. This is so cool. Watch, here it goes. Boom. Oh my gosh. That was so awesome. Look at that. That totally worked, right? 90 degrees. I love it. I love it. I love it. Okay, cool. So that worked. I'm pretty happy with that. All right. Well, now I'm feeling pretty convinced. Now, again, you know, we'd want to do a precise proof before you'd want to believe it all the time. But at this point, just kind of go with trust me on this one. So again, what we're calling here, again, this is what we call the Inscribed Angle Theorem. Right? The Inscribed Angle Theorem. And the way it works is, so if you look on this picture right here, so I've got angle B, right? So angle B here is an inscribed angle, right? So angle B is from here. Ooh, I didn't draw that very well, did I? So this is my inscribed angle, okay? Angle D is my central angle, okay? And then the arc that they both intercept is this up here, right? So the arc up here is the one we care about. And so the formula just looks like this. The measure of angle B is equal to 1/2 the measure of angle D, right? Measure of angle D, right? You can also, sometimes people write it this way too. Sometimes people talk, rather than measure of angle D, you could also specify it in terms of this arc right here, the measure of arc AC, right? See how I could do it that way too? So, you know, because since the arc and the central angle is the same number, right? I could talk about this and use the measure of the arc instead of that central angle. Either way is fine. You just two different ways of thinking about it. And depending on which way you go, sometimes rather than dividing by 2 and others multiplying times 1/2, you're multiplying times 2. Depends, you know, whether you're going from one to the other. But just remember that the one is twice as big as the other, and take it from there. Okay, so let's come back to our initial question here. So all we got to do is say, look, 42 degrees, double that, gives me R. So hence R is just 2 times that, which is 84 degrees, right? There's my central angle, 84 degrees. All right, now the other thing that comes up sometimes is you're going to see some where we're going the other way. Well, okay, see, look, this time we're going from the central angle back to the inscribed angle. Okay, well, so rather than multiplying times 2, we're just dividing by 2, right? So this angle right here, right? This right here is just equal to 112 degrees over 2, right? 112 degrees over 2. Hence, that angle would be 56 degrees, okay? If we're trying to find that inscribed angle, it's just 56, okay? So again, you're either multiplying or dividing by 2. Just kind of think about, which one you're going from. Just remember, the one that's touching the circle rather than the center is going to be the smaller one. All right, now let's take a look at another one real quick, which is this guy up here. Now, it's starting to get a little more complicated. So again, you're probably going to want to think about stopping and sketching some of these. Give yourself some time, make your life a little easy. Just get yourself some scratch paper and do this. Okay, but I'm just going to use this just in the interest of time. So I've got QSR. Okay, QSR. This is the angle right here I'm trying to find. QSR, right? QSR. Okay, now, oh boy, I know this and that, and there's actually some clever things you could do with like isosceles triangles and things like that. But there's actually an even simpler thing we can do, and that's to notice that when you go around, 360 degrees, right? Here's 360 degrees. I know 98, I know 142. Well, therefore, because it's 360 degrees all the way around, angle P right here would be 360 degrees minus 98 plus 142, right? 98. So, well, it turns out 98 plus 142 is just equal to 240, right? 360 minus 240, we finally get 120 degrees, okay? So this is 120 degrees, right? So that's 120 degrees. Well, if this angle here is 120, then this arc is 120, and QSR is half of that. So therefore, this angle right here, from there to there, right? From there to there is 120 over 2, which is 60 degrees. Okay. All right, let's do another example. Okay, and all right, here's another one. Now, this is one where, again, we're trying to find EFG. So this time, it's the inscribed angle I'm looking for. Now, let's carefully figure out what that is. Okay, I'm just going to do it in red, right? So EFG, so it's over here. And again, a lot of these problems, I gotta be, it's a lot of time it's just about carefully defining what you're looking for, right? Just draw, if it's not obvious right away, just draw some figures and then just start playing with it. What can you figure out? It's not always obvious how you're going to use what you do. Just start writing stuff down until suddenly you know enough information. And this is a perfect example, right? So, okay, so here's that angle. Well, here's a 71 degrees. I mean, one thing I see right off the bat, let's just start writing some things down we know. Well, hey, you know what I do know? I know that this is 180, right? So if that's 180, then this is 109 degrees. Okay, that might be helpful, right? Right, this is 109 degrees from there to there. What I also happen to know is this. Look, if that's 190 degrees, then this arc here, right, is 109 degrees, right? This is 109 degrees. Now, why that's helpful is because, look, this angle just marked this out. Look, so we're going from here to here, right? Boom, boom, right? There's an angle, right? From there to there. This angle touches that arc, and that's what we're really looking for. We're looking for, anytime you see an angle like this where it's touching the circle, you're probably going to be looking at what the arc is. It's almost like you got a flashlight. Think of it as a flashlight here, and it's shining on this part of the arc. So we're going to want to figure out what that arc is. We can figure out what that arc is by figuring out what the central angle is. Okay. Well, F has to be 109 divided by 2, right? This is half the size of the central angle. So half of that is 54.5 degrees. Okay. Now, I'm just going to really briefly, without getting into a lot of detail, turns out there's another way you could have done this. And again, we're always looking for more than one way to do things, right? Remember that radii are always equivalent in length, right? So they're congruent. So because those are congruent, that means these angles are congruent. Remember from isosceles triangles? Well, since those two are the same, and this is 71, the only way that works is if this is 54.5, this is 54.5, right? 50, that's 109, 109 plus 71 gives you 180. Okay, another way you could have done it, but the long and short of it is 54.5. Okay, another example. We're just flying through some examples here. Okay, another one. Again, this time, look, we're trying to find the measure of I, right? This angle right here. This angle, this angle. Well, shoot, if only I knew what this arc was, I would be so happy, wouldn't I? Well, I know how to find what that arc is. Here's 105 and 124. Well, this arc must be, right? It's once around a circle, right? So 360. So this is 360 minus 105 plus 124, right? If you work all that out, it turns out that this arc right here is 131 degrees, okay? Well, if that's 131 degrees, this is half of 131 degrees, right? This is 131 over 2, right? Which is just 65.5, right? So that's another quick one. Again, a lot of this stuff, you just look around, see what you can kind of play around with. Use all the different relationships we've had. Okay, a little different thing we're going to look at now. It turns out what we've been doing, right, we always had the same arc that we were looking at and the same angle coming into it. Well, sometimes what we're going to have is two different angles that are intercepting the same arc. In other words, and that's what's happening here. Notice what it's asking for is the value of x. Now here's an x, right? And we happen to know this is 40 degrees. Well, now this will look sort of like, hey, I've got a, like some sort of a, I don't know, figure 8 going on here or something. But really, the way you want to think of this is imagine that I've got this angle keep going. So with these kind of problems, imagine it just keeps going. Focus on that, and then you've got another angle over here, right? That's coming from there. See how? So think about the yellow as an angle coming to the circle. Now notice that they're going on to the same arc. Well, shoot, because they're the same arc, wouldn't that mean that they're the same size? These angles, they got to be the same measure, and that's actually true as well, right? Because remember, there was nothing in our proof that said I had to draw the arc in a special place. So I've got some special examples here to show you. This is pretty cool. So here, I'm back to this 45 and 30 degree thing. 45 degrees, 30 degrees. Now this is two circles. The circles are the same size, but these angles are different, right? So this one was, so I did this template before the talk, right? So what I did is, these are all 30 degrees. This is 30, 30, 30, 30. All the way around, those are 30. This other one, each one of these is 45. There's 45, 45, 45, 45. Each one of these angles that I drew here is 45 degrees. Each one of these, 30 degrees. Notice that they always intercept the angle that's the same side. Now this is obviously bigger than this one, right? Because it's a bigger angle. But notice they all hit the same arc. And that's what we're going to use here. As long as we're hitting the same arc, this blue arc here, then I know that this angle has to be the same as that angle. Which then means that we can set up an equation, right? 10x equals 40 degrees. Well, if 10x equals 40, yeah, I can do that easy enough, divide by 10. X equals 4. How cool is that? All right. So we saw that. Here's another one. Okay, whoop, another one here. You didn't see my answer too quickly there. All right, and again, now we're back to some similar things we had before, right? Where we have, again, this time we're trying to find the value of x. So x is right here. What we're going to use is the fact that they both go to the same arc. They're both going to the same arc. Well, because of that, this is 41, so I know that this angle here has to be double that. This is 82. Okay, that's not so bad, is it? We just have an equation, 4x plus 78, right? 4x plus 78 equals 82, right? All we're going to do is divide by 78, or subtract 78, subtract 78. I get 4x equals 4. Divide by 4, x equals 1, right? So therefore, x equals 1. Now this is actually in degrees, so I should have said degrees. And there you go, okay? And that is it for today. Now, I did kind of run through these examples pretty quickly. So what I would suggest is go ahead, try the IXL. If you're getting stuck, come back, rewatch this video, and see if you can find an example that helps. Or, of course, there's always the examples in IXL that can help you too. All right, guys, that's it. We will see you next time. Have a great one.